This is one of the flows that we have institutionalized inside of Micron. To, to summarize what first silicon success actually, we basically tape out a chip, and we don't want to be in the business of retaping the same chip because we basically discovered some bug there. And identifying finite state machines in the code is, let us say, not the only thing that is actually needed to enable first silicon success, but that's, let us say, a necessary condition, but not necessarily a sufficient condition, but that's basically a prerequisite. So here I would basically go through the problem, the approach that we have basically used, and some analysis against some of the benchmarks that we have internally have. So enabling first silicon success is the goal of all of the design verification when it comes to like certifying and qualifying the ASIC products. And they basically has like two things. One is getting 100% code coverage of the structural coverage, and the second is like trying to identify whether the device is actually functional. So that's like trying to meet 100% functional coverage. That kind of like make sure that the device is actually not misbehaving and it's doing what it is supposed to do. And FSM identification is one of the key coverage objectives. And the baseline industry tools that we essentially use sometimes do not capture all the different FSM implementations. Now, not capturing FSM implementation leads to like two things. One is like the device might end up being in a deadlock, which is actually not captured during the verification. And the other thing is it might actually have redundant logic, which leads to like issues in like, suboptimal timing. You might have like circuits which are redundant and like just consuming unwanted power. And there is like wiring on the circuit, which probably shouldn't be even there, but it still exists. So the solution is like trying to bring in the concept of what is happening in the software world on the compilers and trying to treat hardware as a software and see if we are able to like identify the FSMs as good as in the software world. So typically in the hardware world, what does this FSM basically means? Like, you have this device of this, any of these vending machine, it basically takes some money and dispenses something. So that's like a classic example. So technically, like there is a state, and like when it receives an operation, it goes ahead and does something else. And the advantage of having the FSM based design for the hardware is like, one is it's kind of like predictable. It has like certain states, each states has certain behavior and certain output. The coding for the hardware, the abstraction, the way in which the software equivalent of the hardware is written is like is quite simplified. The coding is like, it's quite readable, and it enables like simpler verification. And essentially like also the device also like becomes manageable in terms of like the power consumption, resource consumption, communication, area allocation, so on and so forth. So in the typical electrical engineering world, the FSMs are like identified, kind of like classified into two different machines. One is a Mealy machine and the Moore machine. Now the Mealy machine is like the machines which basically represent the protocols, which is like very high responsive protocols. And the Moore FSMs are basically trying to like used in class of devices wherein like it's not like a fast responsive output, but the timing of the device is like absolutely predictable. So the Mealy FSM machines have a complex logic implementation, harder to verify, but the response and efficiency is very great. The Moore FSM, on the other hand, like, it has like slightly large number of states and larger logic, but it's a simpler design and it's simpler to verify. So both of these two actually exist depending on the use cases that we actually target. So we essentially like go ahead and try to come out with MLIR kind of a dialect to capture all the FSMs. So there are dialects already existing. The Moore dialect, which is another MLIR dialect, which basically captures the system Verilog constructs, but that's actually not complete. It captures only like 80% of the constructs that are available today. And there are like a lot of other syntaxes which has not been enabled, and it requires some more community effort. So rather than improving on that, which also like some other hidden foundations of which we have no control, so we internally developed this YRAR representation, except for like, maybe three different constructs of system Verilog. Almost everything else is captured here, which is good enough for for running our business there. And it captures all the different type settings that are already there in the system Verilog. And then it also bring in the MLIR concepts of like static analysis, dead code elimination, canonicalization, and all of those things, which probably is not completely available there in the Moore dialect. So these are some of the basic operations that are already there in the YRIR intermediate representation. And these are basically used in the case of like the FSM extraction. So one of the example is, so this is one of the, let us say, simpler code. And most of us can figure out like there is an FSM there. There's a case statement and there's a transition happening. But most of the methods that exist actually today at the industry don't necessarily identify the FSM that is already there. Now it's kind of like hard to figure out why these commercial tools don't necessarily extract this. Our best guess that we can actually make is like, if you have a state, and let us say the next state also like refers to the previous state with the same variable, the the compiler that is actually running in of some of these existing tools might have an issue. And they might also have an issue in like the synchronous and the asynchronous clock and the reset signals. But then let's say that, if the same code were to be rewritten in a different form, in a slightly verbose way, these compilers essentially go ahead and like are able to extract the FSMs. Now, the problem is that FSMs can actually like appear in multiple different forms, and it's very hard to like go ahead and rewrite all the FSMs everywhere, because it's kind of like very stylistic and idiomatic depending on the way the designers go ahead and write. So the alternative was that we ended up using the WireAir approach, and then with with this original code which the existing tools are not able to like decipher, like our approach essentially was able to like go ahead and say that, okay, you have a case statement, and then it kind of like maps into that. Yes, it kind of like maps into a switch, and once you have a switch, you can kind of like identify like, it kind of like comes out with this representation, says, yeah, this is a switch, and then you have these states. And once you have this representation, we can basically go ahead and construct a truth table and then identify it as an FSM. Now, in case this is not identified as an FSM, the compilers will basically default this into as lines or statements. And then the coverage is identified as like, yeah, whether it was covered, whether it was hit or not hit. But the truth table logic is kind of like totally gone. And once the truth table is not there, redundant logic, and then let us say that, if there was a race condition or deadlock, such kind of identification is not even possible. So one thing is once you have the representation, the second part is basically the extraction of the FSM. So the extraction of the FSM is identify if there is basically a switch statement there, identify how many operands are there, and if that operand is basically reassigned to something else, then there is a state transition, and essentially go ahead and build the truth table. So that's pretty much the algorithm that we have over there. It's a rule-based algorithm. And once this rule-based algorithm is basically constructed, we went ahead and like tried to find out whether this actually does deliver what we actually want. So this is like, I'm defaulting back to the same example where this is like the standard failure case in most of the IPs that we have. This is the WireAir representation. Now parse this WireAir representation with our algorithm, and this finally like delivers identify this as an FSM, delivers this that, this is that state transition diagram. And then once the state transition diagram is there, you can actually map this into a truth table, and then the coverage optimization for this particular truth table can be done. Now, to what extent all of this actually works. So we basically looked into some of the most frequently used IPs, And from that, we identified that there are about like 8 most frequently used FSM implementations. And we basically we went ahead and remodeled the system Verilog code based on the FSM implementations that are already there in this most frequently used IPs. And our approach was able to basically go ahead and extract the FSMs from all of these 8 templates. But the state of the art tools that are already there, they probably miss out on the top 3 most frequently used FSMs. So, and the peripheral thing is that we also happen to be able to extract this at higher levels of efficiency. But then being able to detect the FSM is of a higher value add than the runtime in itself, because the runtime is, as far as the extraction of FSM goes, it's done only once. But then most of the time is actually spent in the design verification, trying to simulate the test patterns, trying to hit these FSMs. And if you can't even identify what the FSM is, there is no way that you will be able to go ahead and cover them. So essentially, with this particular approach, we basically increase the fidelity of the design verification, because one is that it essentially knows that it's not just it's not just statement, it's not just a bunch of statements. These bunch of statements agglomerate themselves as an FSM, and it has to drive up the truth table maximization coverage of that set of lines, and not just going ahead and trying to hit those lines. Then the other advantage of our approach is that one need not essentially go ahead and rewrite an FSM that's already there just to right size it into the commercial tools that are already available there. So it could basically take the way in which the designer would have written. And then along with this, since it's kind of like an MLIR dialect, it also provides the dead code elimination, which means to say that you get rid of a lot of logic which shouldn't be even there, improves the silicon quality. And well, as I already started at this talk, so this is not a sufficient condition, but this is a necessary condition amongst a long step. But if we don't have this right, we obviously are kind of not fully guardrailed. Yeah, thank you.
So let's thank the speaker. Very nice and in time and fascinating talk. A lot of questions, I'm sure. We have time for a bunch of questions. Yeah, question there.
So what is the exact reason why this approach is much better than others existing state-of-the-art methods? Like, is it your algorithm to detect FSM that is the key, or is the general representation that you have in the form of a MLR dialect that is the key, or is your lexer, which is lexer or parser, which is basically parsing from different high-level constructs to a generic MLR IR is the key? Like, which of these three is the reason why this is better than existing SOTA methods?
Okay. Well, the only other IR which as I said works 80% is the Moore dialect, but the Moore dialect is kind of not complete. It's incomplete, and pretty much because it is incomplete, it's not able to go ahead and extract a lot of the FSM straight away. I mean, in the sense, it's not about even the FSM extraction. There are certain system Verilog syntaxes it doesn't recognize, so it just says that it is unknown. So technically, there is no baseline. And for the algorithm to work, the algorithm is, I would say, it's relatively simple, but the heavy lifting has already happened on the intermediate representation, because we don't essentially have any community support. So this was actually done totally internally in the company. You can basically assume that it's basically a Python code which is parsing the YRI representation.
Thank you.
Dr. Didi.
Yeah, just an observation in your table. If you go back on the right hand side, I saw everything taking 200 milliseconds.
So this is basically coming from one of the tools, and let us say that the 200 milliseconds also includes the timing of the license initialization and other things. So this is not locally running on our machines. It's a cloud-based thing. So yeah,
Yes.
it's put it.
And the numbers you see on the left is all coming from your net code elimination or comes from that kind of.
No, no, it's purely the YRIR pass. It's just the YRIR pass.
So the formal verification techniques, don't they address this problem?
The formal verification tools already exist, and they actually operate on limited set of these examples. The problem with the formal verification tools is that it doesn't necessarily scale up. So because of its inability to scale up things, we had to go this route.
So I have one question. Have you considered using ML-based techniques?
Okay, so the ML-based techniques, I'm assuming that you're asking if there is a particular code, can you basically identify whether there is an FSM? Okay, well, there is. I mean, in the sense, it is an interesting research problem to do, but probably it's hard to justify in terms of like business, because one is if there is an exact solution to say that there is an FSM, we would rather go and identify there is an FSM and use ML to drive up the coverage there.
Thank you very much. Let's thank the speaker again. Thank you, Mr. Narayan.